Math 1314, Tyler Junior College, Section 4.5, Exponential Growth and Decay. Exponential growth and decay models. In a lot of natural phenomena, there are situations where a population of items is growing or decaying. Now, when we say population, we don't necessarily mean a population of people. It can be a population of plants, it can be a population of animals. It can be a population of radiation in the atmosphere. It can be the population of a drug in your bloodstream. Anything where we talk about a group of something, we can discuss as a population. And in a lot of those situations, the growth or decay, depending on if the population is getting larger, such as a population of rabbits, or getting smaller, such as radiation decaying in the atmosphere, a lot of times that growth is proportional to the current size of the population. And when that happens, we have what's called exponential growth and decay. Now, why is it exponential? You'll see in just a moment. Well, let's assume that the rate of population grows or decays is directly proportional to the current size of the population. So the more rabbits you have, the faster the population grows. The more radiation in the air, the faster it decays. With calculus, and don't worry, I'm going to spare you the calculus, it can be shown that there's a function that relates the time that's elapsed to the current population. In other words, a function that can answer the question, what will the size of the population be after a certain amount of time has elapsed? So it can be shown that the function relating time t from an initial starting time. So we have to say we're starting the clock now. And the population, which is going to be a function of t at that particular time, has a certain form. The form of that function is f of t equals a, which I'm going to subscript with a 0, times e to the b t power. Both b and t are in the exponent. E is the natural base, so it's about 2.7. Excuse me. Or if you want more precision, about 2.718281828459045. But it's that irrational constant called the natural base. Well, what about the a? Why is it subscripted with a 0? And what's with this b up here? Well, both of the values, the constants in this function, the a sub 0 and the b, have a specific meaning. A sub 0 is the population, or initial population, I should say. Initial population at time t equals 0. So whenever we start the countdown, or the clock, if you will, we're going to start measuring the population at a certain moment in time. That's what this coefficient represents. B, however, is going to be a number between -1 and 1. So it's a small number and probably a decimal. The reason it's between -1 and 1 is because B represents the rate of growth or decay. Growth, if the B is greater than 0, or decay, if the B is less than 0. When I say it represents the rate of growth, it'll be a decimal that can be interpreted as a percent. So for example, let's say that we had a function that models the population of a country that looked like this. F of t equals, let's just say 1 million e to the 0.02 t power. This function has that form, or this model, I should say. And by the way, the word model simply means a mathematical function or equation that mirrors a real-life situation, so it has an application. Think of a model as an applied equation or an applied function. If we had this exponential model, first off, would it be growth or decay? To answer that, you simply have to look at the coefficient of t If it's positive, it's growth. If it's negative, it's decay. So this clearly represents exponential growth. Now, in order to correctly interpret the 1 million, we have to first establish what t is representing. So suppose that t is the number of years since, let's say that this modeled population growth starting in the year 2007. I just picked a year at random. Then the A0 being the 1 million represents the population in 2007. Now, is that consistent with what we said over here? It is. Because if I said t equals 0, and then asked you, if we're in the year 2007, how many years have elapsed since 2007? Well, no years have elapsed because we're still there. As opposed to say, if we were in the year 2010, how many years have elapsed since 2007? That would be 3. So t equals 3 years would be 3 years after this, 2010. T equals 5 would be 5 years after this, 2012. But t equals 0 would be 0 years after this, 2007. This is what's called the initial population, as we said over here. And that's what the coefficient in front of the e represents. The population at the whenever t equals 0. T is almost always defined in terms of a starting time, in this case starting in the year 2007. But what about the 0.02? As we already discussed, because it's positive, this is exponential growth. But if we think of this as a percent by moving the decimal 2 places to the right, this is a 2% growth rate. And that's how you can interpret the numbers in an exponential growth model. Had it been decay? Well, first off, what would have to happen in order for it to represent decay? To be exponential decay, the coefficient of t would have to be negative. So just for kicks and giggles, let's say that that negative 0.02 was negative. What would change here? First off, it wouldn't be called exponential growth, it would be called exponential decay. Secondly, the b would be negative, but how would that be translated? It would still represent 2%, but it wouldn't represent a 2% growth rate. It would represent a 2% decay rate. Can a population decrease in size? Of course it can. If the death rate of its members is greater than the birth rate of its members. Or in other words, if the speed at which things are leaving the population is greater than the speed at which things are coming into the population. So it is possible for a country or any other population to have a negative growth rate. So what can we do with these? Well, we'll see in the next video. But one thing that models are good for is using past data to attempt to make predictions about the future. We'll see an example of that in the next video.